Okay, so we have a good bunch, good load of technical bunch this morning introducing, you know now what the quantum annealing, you know what the quantum gate model. Now our talk, now our keynote talk from D-Wave. D-Wave is a company that works with quantum annealing and quantum circuits, mostly quantum annealing, but let me introduce our keynote speaker for today, Dr. Catherine Parks, Principal Technical Account Manager at D-Wave, D-Wave Quantum Inc. She is assisting clients in building quantum optimization applications for commercial and research use. So she has a PhD in applied mathematics from Montana State University, and she focused on adapting machine learning algorithms for scientific imaging. Since 2020, she has been focused on building quantum computing applications for different types of quantum hardware, including the D-Wave quantum annealing and hybrid technology that she is going to talk with us today. So please join me welcoming our expert, Dr. Catherine Fox.
All right. Thank you, everybody. Thank you for coming and listening to my talk. I'll get in frame. So we're going to talk a little bit, we're going to pull things up a little bit of a higher level, but then when we get into some more specifics, we can kind of dig deeper. So we're not going to do much in terms of like algorithms for this talk, but we'll talk kind of more about like what the state of technology is, especially for D-Wave, what folks look for when they're trying to build applications on quantum computing systems, and things of that nature. So, okay, really sort of like big picture, like how do we describe what a quantum computer is? And the way that D-Wave describes quantum computers is summed up in this statement. Energy efficient computers tackling complex problems. So we talked a little bit earlier about how, quantum computers can work on the same classes of problems as classical computers, and they can, and that's really amazing. But for the state of technology now, we often try to use the quantum computers for problems where standard computing methods kind of are insufficient in some way. And we'll talk about what we look for when we take on projects. What does that insufficiency mean? Because it can mean different things based off of different types of systems. This image is pretty fun. This is a picture of the casing for our Advantage 2 quantum processor. So the actual chip is about the size of your thumbnail. This housing here is about this big, and that goes into a really big box and gets very, very cold, so we can perform calculations. We've also talked about different types of quantum computing technology, and well, we're being recorded. Usually can you all see this okay? It's a little small. We might be able to hit one of the lights and make it show up a little bit better, but if not, we don't have to worry about it. Is that better? Probably terrible for the video, huh? Lights on? Okay. Okay. Okay, so when people talk about quantum computing, they're usually talking about one of two different modalities. There's lots of new research kind of coming out, but I would say that these two methods are the more kind of commercialized or leading to commercialized versions of quantum computers out there. Ibrahim was talking about building problems for quantum annealing type computers. And I'm sorry, Mustafa was talking about building algorithms for gate-based quantum computers. In terms of applications, the community sees these as very different purpose machines for different goals. So for example, for gate-based systems, we really look at solving problems that are posed as some form of like a differential equation is typically the type of problem that we target with these systems. So that comes into like fluid dynamics, quantum chemistry. When you're like trying to predict the quantum properties of an actual molecule, you'll want to use a gate-based algorithm for that. Quantum communication, quantum teleportation, that's sitting in this camp with the gate-based systems. Quantum annealing is really built specifically for combinatorial optimization problems. Where that shows up, and we'll see some examples of that in my discussion, is problems that look like scheduling problems, routing problems, something where you are resource constrained, so you have to make choices about where you're going to put those sorts of resources. So we're looking for problems that have some flavor of a yes, no type decision variable. And then, of course, nothing is cut and dry in this world, so we have some areas where applications may be suited for quantum annealing or for gate-based systems, depending on how they're posed. Machine learning algorithms, or the intersection of quantum computing and machine learning algorithms, fall into that camp. Sometimes they're well posed for annealing systems because they come in the flavor of a combinatorial optimization problem. Sometimes they're better posed for gate-based systems because they're operating on quantum data, or they have some aspect of the actual quantum algorithm that can be tuned. So there's lots of kind of different sorts of overlap there. For the majority of our talk, we're going to focus on, or I'm going to focus on annealing systems. D-Wave does have a gate model program, but when we work with researchers and when we work with commercial clients, D-Wave's philosophy is to promote technology that can be used right now. We have annealing quantum computers available on the cloud today, and we'll use some later today. So most of the time, we move clients towards that annealing technology. We don't have a gate-based system available today. We have submitted quite a few papers kind of along that lines, but we won't really put one up available for public use until we see that it's robust enough to be useful. So I kind of expect that to happen in the future, sometime in the future. Okay, so what is quantum annealing? So in the chip, we cool the quantum computer down to a temperature that is oftentimes colder than space. Usually the coldest part of the universe, known universe, is inside a D-Wave quantum computer. We do that so that we can get the quantum mechanical effects that we've been talking about today in the actual chip. And what that means is if we're able to do that in a nice way, we can apply what's called the adiabatic theorem of quantum computing. So how that works is basically we start the chip in a nice position, in what's called a ground state position, where all solutions to the optimization problem that we are interested in have equal probability. So we spread out a probability distribution over these ground states of all the qubits that we're going to kind of use in this computational basis. Then we slowly move from this ground state, where everything is equally probable, to the complicated problem that we're interested in such a way that we're able to use quantum tunneling, superposition, and all of those things to model the probability distribution across this now complex surface and stay in the minimum ground state. That can be a little tricky to kind of like conceptually visualize. I'm a mathematician, so I think about it as almost like a topological space. that you're morphing through this nice way, and that topological space is what the quantum computer sees as we kind of move through this process. You can also think about this in terms of an optimization problem where the space that you're traversing is called the optimization landscape. It's defined by an objective function. When we solve an optimization problem, whether we're using classical or quantum annealing, classical methods or quantum annealing methods, we can model that problem thinking about it as a topological surface, and a hiker along that surface represents the computer's state, so where the computer is investigating at any given point in time in that algorithm. We'll see a couple of different algorithms here. We already kind of talked about simulated annealing. We talked about quantum annealing, but there's also a greedy algorithm, which does the most obvious thing you can think of. Wherever you start, you just go down. So if we have a objective function surface that looks like this yellow line here, and we have a variable state here, and our hiker represents where the computer is focused at any given point in time. If we run the greedy algorithm and we start it here, the hiker's going to go straight down, and then it stops in a local minima because it can't go down anymore. So how computer scientists kind of get around this is they run this multiple times with many different starting positions. That can get computationally complex as your surface gets more and more complex. And there's no guarantee of finding the ground state solution or the lowest state, the global minima. Simulated annealing, we kind of talked about this where we're kind of like jumping around. The way I like to describe this is very similar to the greedy algorithm. However, there's a probability distribution kick that kind of spits you in and out of the position that you're looking in according to some, and this is where the annealing comes in, you kind of like turn down that probability kick as the algorithm runs. So what that sort of looks like is you get this sort of jiggle in the space that you're considering while you're still trying to go down. So that jiggle can push you out of a local minimum, but it doesn't guarantee that you're going to find a global minimum, and you can do the same thing where you start this in many different places and you build your own probability distribution. I did this 100 times, and out of those 100 times I saw this, and you do it one by one. Maybe you introduce some parallelism, etc. Quantum annealing looks at this problem in a very different sort of way. So for quantum annealing, what the quantum computer sees is first a ground state where all solutions are equally have equal probability. So we start off with this very nice surface and a probability distribution spread across that entire surface. Then we slowly introduce the problem that we're interested in, and the hope is that probability distribution will start to coalesce where the minimum value is. I said that's a hope, it's not a guarantee. This isn't an exact algorithm. We're not guaranteed to find the global minima. We're still getting a probability distribution. And in fact, if I was going to do this image with a little bit more grace, then I might have like 75% of a hiker over here, and then maybe I have 25% of a hiker over there. What's different about this algorithm, first off, is how we do the computation. Hopefully that's clear. But what's also different, with all of those other algorithms, I have to kick off multiple processes to build a probability distribution, to build a heuristic model. You can do that with one shot with quantum annealing. So depending on your problem and its complexity, that may be useful, it may not be useful. In our example, we could see where the minimum was, so maybe not useful for an example like this. Okay. So that's why this picture is kind of why we say that when we're looking at quantum optimization, it's very different from the way we look at things before. Simulated annealing is often used. You'll read papers where simulated annealing is used to compare against quantum annealing. That's great. It's a nice, simple benchmark. They accept the same class of problems as a quantum annealer does, but the core computation is very different. Okay. Any questions? Amir, how much time? When should we pause? Or am I just going until I'm done? Okay.
After that, we have the lunch.
Yeah, so whenever I'm done, we're done?
Whenever you're done with no questions, you can take the lunch.
Okay. Sounds good.
How much is all that depends on your initial state?
So for yes. Yeah, because it's not on the mic. Okay, so the question was, how much of this depends on the initial state? So the entire algorithm uses the same initial state for the quantum annealing system. For quantum annealing, we don't change the initial state. So it's always the same initial state. The entire algorithm runs based off of this initial state. So I guess I haven't ever really thought hard about like what would happen if you changed the initial state. We don't have the controls available for you to change it, if that makes sense. We're always starting in this state where our qubits are in their ground state, and we have an equal probability distribution spread across all of the qubits that we're going to activate.
So I have a question about the part that you said it's not guaranteed at the time. So to me, it looks like this is like an analogy that just thought of was we just have like a hole and it has some sort of complex shape. And with simulated annealing, you just pour water randomly somewhere, and the water goes and gets stuck somewhere in one of the local minimums. And here you have this nice ball, and then you try to dent it, like different parts.
Yeah.
And then you hope that the water that is already in there goes into the. So I think it depends where you start denting this ball. Right?
Well, so yes and no. Okay, so the question is like, is this the same? So what you described is how we would think about it if all of the attention has to stay at the surface level of the probability distribution. What I didn't talk about was the quantum tunneling piece. Quantum tunneling comes into play during the computation where we can dive under a dent, basically, the high part of a dent. That happens at the qubit level, and it's fairly difficult to describe what happens at the optimization surface level. What it looks like is some things just kind of jumped to the other side of that ridge. So yes, we're thinking about kind of like massaging the bowl, but our surface doesn't behave the way we think it should in terms of just water in a bowl. Does that make sense? Okay. Cool. Okay. So bringing it back to like the different types of quantum computing system, what I described was quantum annealing. Gate model system, you have to think about how gate models interact with their qubits and applications in a completely separate way. So what I just described doesn't apply to gate model systems, only quantum annealing, and only combinatorial optimization problems. So because of that, we have sort of D-Wave has kind of like developed a little bit of a framework to kind of like identify different types and like classify different types of quantum technologies. There's quantum annealing systems, there's gate-based systems, There's gate-based systems on different types of qubits. There's quantum technologies that don't correspond to quantum computing at all. There's all sorts of different things that have the word quantum next to them right now. So it can get a little bit confusing in terms of like, okay, which of these should I pay attention to? Which of them make sense to kind of like look forward for the next 5 years? And this framework we called Quantum Realized. You'll see it on my t-shirt and all over the D-Wave website if you go look at dwavequantum.com. But there's like 3 main parts to it. First off is the technology itself. So is there a record of this technology doing something that we can't do with current state-of-the-art methods, basically? When you're talking about quantum computing, that means, is there a record of this technology doing something that classical computers can't do in a reasonable time frame? And then the next pillar is availability. Is the technology available to use now, and can I use it reliably? And then the final pillar is it commercial? So does that mean, can it be used for something that is useful enough in a customer environment? So those are the 3 pillars that we propose for measuring different sorts of quantum technologies. And we're going to go through the different ways that D-Wave satisfies these pillars. First is availability. So D-Wave is a full stack quantum computing company. That means we build hardware. So we have hardware, and we'll talk about where the physical hardware is located. We have 6 generations of annealing quantum computers. These Advantage 2 systems can have up to 4,400 different qubits. We just announced a new system that's connected online literally today. That's an Advantage 2 system that has 1,200 qubits in Huntsville, Alabama. But we have these kind of across the globe. Then we also host our own cloud service. So how people can actually access the quantum computers is through our Leap cloud service. We also host the hybrid solvers that Ibrahim was talking about through our cloud service as well. Then we also build a large suite of developer tools. And if you stay for the tutorial later today, the hands-on portion, you'll be using some of those developer tools. These are open source Python tools called Ocean. We have examples of applications as well as all of like the modules and code base to build your own application. Then we also offer professional services. Quantum computing is a fairly new field, and as I think we saw earlier today, for every 3 open positions, there is 1 qualified candidate to fill it. That includes building applications for quantum technologies. So we have a services team to kind of help train as well as build projects for folks. I'll talk a little bit more, because I said availability. I'll talk a little bit more about how available our systems are. We have 3 nines of uptime. That means 99.9% of the time you'll be able to access a D-Wave quantum computer and send a problem through with real-time results. Problems going through our system, because we're running the same algorithm each time, the quantum annealing algorithm, it takes less than a second to run that algorithm on our system without queuing and things like that. So when you use D-Wave systems, you get a response back fairly quickly, which is how Ibrahim was able to do some of the work that he did on query optimization. Focusing just on research, so D-Wave started in '99. Our first system was installed. Our first commercial installation was at USC in 2011. So we've had systems available for researchers to touch for quite some time. We started our cloud services somewhere, I don't know the exact date, somewhere around 2020, maybe a little bit before 2020. So we have a significant number, like catalog of research based off of our systems. We also have a pretty robust publishing body at D-Wave itself in our research and development department. And we've partnered with Los Alamos National Lab. ULIX Supercomputing actually purchased a system last year. Ornal, NASA, as well as USC ISI, they have a computer at their lab as well. Oh, and I just said that. Okay, so the systems that we have right now, this one was just installed, so my slide is out of date because it was made live today. But the Huntsville, Alabama system is turned on now. We have one set up in USC Monterey. We have one in Germany that is a private system, so it's not available on the cloud right now. We just announced a collaboration with folks in Italy to put a public system there. And then we also have a few different systems available in our R&D offices in Burnaby, British Columbia. We've signed like an MOU to explore something in Korea. Yeah, we don't have a system in Japan currently. Love to put one there. Yeah. So basically, when folks sign up for a LEAP account, they can touch any of the public systems on the cloud. Just a little bit of a background of our relationship with USC, where Ibrahim is posted. In 2011, our first system was installed. We did an upgrade in 2013, 2016, another upgrade, 2022. We signed up for the cloud, and right now they have an Advantage system that's available. And it's reaching, this is kind of a fun fact, it's reaching the oldest, like the longest cooled down system that we have record for, which is pretty cool. So it's been operational since 2022, which is really, really amazing. So this is what the system looks like. This is the picture of the system. Do I have I think this is, we'll just go with this. This portion up here is a server rack, basically. So this is where problems come in and then are programmed on the chip, which lives in here. So the chip lives in a big box that's like about this tall, with a chandelier that like does the cooling part, and then that case where the chip, which is the size of your thumbnail, actually sits. At USC, there's been like lots of different sorts of research that's come out using the system, including Ibrahim's paper on joint orderings. And then I also chose to highlight the spatial regionalization paper that Amir works on. But the system supports research in applications of quantum computing as well as quantum physics. So there are researchers at USC working on the quantum physics side. There are researchers that are looking at computation in general, and then there's also researchers that are looking at applications of quantum systems. And I just wanted to also highlight how that research has changed with the different iterations of D-Wave systems over the years. So, for example, satellite problems, so optimizing satellite placement, essentially different flavors of that, have been studied in the quantum computing space for quite some time. These papers that I picked out are specific to quantum annealing. So in 2018, we had a paper that used the D-Wave 2X and basically said, okay, yes, we can write this problem as a QUBO, but the hardware isn't quite ready yet. to give us meaningful results for that QUBO in 2018. In 2020, we looked at using the 2000Q system, and this paper looked at comparing real-world application sizes. Same sort of results. Okay, yes, we can do this. We can look at what this would look like for like a real-world problem, whereas these were kind of like still kind of like a toy problem example. But the hardware still needs to be better. In 2023, we used this group used a hybrid solver and saw, oh, we got cut off a little bit, but better solution quality and timing than classical methods for the types of problems that they were looking at. And then last year, 2024, this group looked at the Advantage 2 system, which is our 6th version, and we had a prototype available for folks to use. And what they saw was that this system was more performant than simulators using a method called QAOA, quantum. Thank you. I was like, where's the approximate go? Is it first or is it second? Yeah, yeah. QAOA. Right, right. So this was a very interesting result, and also on realistic examples as well. Maybe not the example where they got the result for QAOA, but they did extend it past what you could do with QAOA. So very interesting paper. And the question is like, this was on a small prototype example. Now we have the larger chips available. What comes next for these classes of problems? So where do we push this research moving forward? And so speaking about different sorts of research, there's research in different sorts of camps. So I'm going to talk a little bit about the research that D-Wave does with these systems, specifically also the research that was done with the Advantage 2 system. So the type of problem we'll look at is an Ising spin glass problem, and that's a very physics-based problem that deals with magnetic materials. So we have a history of publishing about these Ising spin glass problems. We have a section of our R&D organization that works with external researchers at LANL and ORNL on this class of physics problems. In 22, we showed that you can model quantum dynamics in a 5,000 qubit programmable spin glass. And the results of that paper basically are to look at like the scaling effects of the computation. So here, the dashed line, or sorry, the solid lines represent the theory, and then individual icons represent experimental results. And the hope is that the better the processor, the more you match the theory of how these are going to go. And so this was the result. They compared simulated annealing, simulated quantum annealing, as well as quantum annealing, and we were matching pretty close here, which is exciting on our last Advantage system. So again, we're not matching quite as close as the simulated versions, but we're also able to kind of match some interesting dynamics at a faster scale than over here. So shift this way. We took this paper, this work, and we extended it when we released our Advantage 2 system. So we extended it in the types of problems we were looking at. Before, we were just looking at spin qubits basically in a single direction, a 1D representation. So now we're using 2D and 3D representations of these qubits connected together. We also extended the size of the simulation, so 16 qubits down to 567. the evolution time, so how long we kind of were measuring the dynamics, as well as different sorts of material properties. And then the question was, can classical computations, that simulated quantum annealing, and then other sorts of tensor methods, keep up with what we can measure on the quantum annealer for these problem classes? And what we saw was that they can't, and basically they can't at an aggressive scale. So what we were able to show was that for certain classes of these problems, the tricky ones, so difficult lattices, a scale that would be sort of like reasonable and very fast evolution times, we were able to solve certain classes of these problems in 20 minutes compared to an extrapolation of how much time it would take on the frontier supercomputer, which was over 1 million years, to solve the same problem that we can solve in 20 minutes. Moreover, if you map that to the amount of electricity required to run the systems, our electricity is less than $1, and the frontier supercomputer to run that same computation would be more than the global annual consumption of electricity. This paper is available on actually it was published in Nature. It was available on arXiv last year. So it's available on Nature. It's linked to on our website. It compares different tensor methods to quantum annealing. I'm not going to lie, it's a pretty dense read. Over 50 pages of physics and computational theory. But it is available if you want to take a look. So this sort of research was enabled by special features that we've put on our annealing systems. The types of features kind of allow you to control the quantum annealing algorithm, basically like how those transitions happen. Remember we talked about like, okay, you have kind of like an equal probability state and then you kind of like morph it into something more complicated. How we do that translation can be controlled in the quantum annealing algorithm. I would call these advanced features. And they're not usually stuff that we see on a commercial level, people using to solve optimization problems. So when I work with clients, commercial clients, what we do is we use the quantum hardware, but we use the quantum hardware with standard optimization techniques. And those are included in our hybrid solvers. When we do that, we're able to kind of target lots of different types of clients, lots of different types of optimization problems. Here are some examples, and we'll go through a few more. For example, Pattison Food Group, we work with them for a workforce scheduling problem. One is for literally putting together schedules for individual sections of grocery stores. Another is scheduling delivery truck drivers to different locations. Ford Otosan, we do a what's called a production scheduling application, matching jobs to machines in a way that kind of minimizes the throughput time it takes to complete all of the workload. For logistics, we had an application at the Port of LA that optimized where we were placing individual cranes to unload cargo ships. Vinci Energies, we worked with them to place, I think it was ducts for an HVAC design inside of a factory. Then NTT Docomo uses our technology to choose which receivers are going to accept which signals in their network. in their mobile network. And they saw a 15% improvement in that network performance using our systems. And then we also have worked with folks in fintech and other places for different sorts of like targeted marketing. So choosing which client base gets what sort of promotion, basically. Okay, for each of these types of problems, the question becomes a little bit different than what we usually ask for quantum computing in the quantum computing industry. The most common question you'll hear in the quantum computing industry is, can we do this faster? But for commercial optimization, faster time to answer, amazing. That's usually quite helpful, but there are other things that are helpful for as well. A higher quality answer in the same time frame may be helpful. Lower cost to answer, also helpful. When we have a large optimization suite, we have to host it somewhere, which means we have to spend some compute dollars on that hosting service as well as the computation itself. Maybe if we lower something, we're able to get a lower cost to answer. Then also, this is an interesting one, additional complexity to answer. A lot of commercial optimization problems are formulated as mixed integer linear programs. And as we talked about, quantum computing uses quadratic terms. So if we're able to kind of enhance the linear program with a quadratic component or even higher, then we're adding in additional complexity into our optimization models, which may be helpful in the commercial sense. So with that in mind, we developed a hybrid solver called our nonlinear hybrid solver, which does a number of different things, and only one of those things relates to quantum computing. So we have a quantum optimization technology incorporated into this nonlinear solver that does things like sends problems to the quantum annealer. It does things like look at things in a simulated quantum annealing modality, all of those sorts of things. What we learned over the last 10 years in terms of how binary problems behave, we've incorporated into this section of our solver. Then we also looked at the types of problems that we're getting from clients, and we recognized that a lot of these problems can be posed as rearranging items in a list or choosing a subset from a list, which points to a combinatorial variable class, which does that in a very nice way, nicer than binary variables. So we incorporated that into this solver. A lot of problems have some form of a mixed integer linear program in them, because that is how we're used to modeling our world, is mixed integer linear programs for all of the commercial optimization engines out there. So we've incorporated that as well into this solver. And we learned some things from what's popular in the machine learning space. We made sure that everything we built in this can be represented as some sort of tensor. So it's also data efficient as we go through. So that's what we build into the types of hybrid solvers. So yes, we take everything that is exciting and unique about quantum optimization, but we also pair it with a lot of standard optimization techniques and revolutionary optimization techniques, the combinatorial variables and the tensor programming, to build an engine that can be very powerful for clients. So one example of what we can do with this is a satellite placement problem. So the satellite placement problem in this example is we want to kind of organize the satellites in an arc nicely, I'll say. So we want to figure out the optimal ordering of these satellites on the arc. So xi is the order of satellites along the arc. Theta I is the location of the ith satellite. DST is the interference between satellites S and T. WS and ES give the east boundaries for satellite S. So what we can do is we can describe this as an optimization problem where we're going to optimize the placements, the ordering XIs, and this is what the optimization problem looks like. Here, this is not an optimization problem that you can fit on a quantum computer, or at least a quantum annealer today. It's in the wrong format, aggressively so. But with the nonlinear solver, the power is in these sections here where we actually have linear terms for our optimization problem. And those linear terms can be included in that solver. And when we do that, we ran some benchmarking results on that model using the nonlinear solver and then using one of the solvers that Ibrahim talked about, the constrained quadratic model solver. So same approach, but we have to do some additional optimization sort of like tricks to map it to a CQM. And these are the results when we do that on different instances. So number of satellites here, the gap between the known best solution here, the CQM solver, so mapping it to a mixed integer quadratic program, and we see that we kind of stall out on the number of satellites we can handle, as well as our gap increases, whereas when we use the nonlinear solver, we're able to handle more satellites, and we get a little bit more time before our time limit, or sorry, before we kind of start losing that median gap based off of the amount of time we allow it to run. So this is what we use for the majority of commercial applications. Because it allows us to do these nice, powerful things and incorporate different flavors of technology into an optimization engine. Any questions?
So how many times do you need to make this optimization for this specific application?
So
you solve it one time, or
yeah, so these were no, so we didn't put the error bound on here, but we solved it 10 times, and we're showing the average median gap.
yeah, I understand. My question is, like in the space, you optimize the location of the satellite's position. So you need to redo the process when the satellite moves.
Yes.
You have to get some data from satellites and then
Yes.
send to Earth to optimize and then send back to satellites
Exactly.
to control their position.
Yes. Yeah, exactly. And so we didn't build a kind of like a dynamic solution. So this is kind of more of like a single shot. We know the positions, this is the timing that's associated with it. But what you can do is you can build that sort of outer loop where you're taking data in from whatever your input is. That's going to determine these values here. Run the optimization. And there's a little bit of a guide of like how long it may take you based off of the number of satellites. So, and the like solution quality that you want. So if you only want, or if you want to rerun this at a quick, step, maybe you only want the optimization to run for 5 seconds. And then you can see that, okay, we should be good until we get to roughly about 20 satellites. And then we start to kind of like lose some of our optimality potentially, according to this graph. If you're able to allow 1 minute of computation time, then you can, according to this graph, push it up higher. Does that make sense? And then you would like re-optimize. Yeah.
I would have a general question.
Sure.
I'm sure you know this unique quantum array of many stars.
Yeah.
There's always a kind of tricky question
Sure.
When you want to do marketing case like this, you take a problem, you solve it with a quantum computer, and you know nothing about the optionality of the solution with a classical system,
Sure.
which quickly gives you like a shitstorm. Someone else does the same. You're posting this with Google and
Yes.
IBM. Is there a sort of a community library, maybe that you have also contributes to, of task where the optimal classical solution is actually known, or is this just like I didn't have a good classical algorithm?
Sure.
You know, this is
Yeah.
risk.
Yeah, for sure. So there's many different like classical like standard optimization algorithms out there. I think MIP-lib is one that comes to mind kind of like immediately. Some of those do have meaning for commercial applications and some of them don't. Some of them like D-Wave uses to just basically like, is this processor better than the next processor? And so we do benchmarking that way. That's right, exactly. It gets trickier when you're using commercial applications because it's not always as cut and dry as like, did we do something faster? We have all of these other sorts of things to kind of consider. And no commercial application that I've been involved in is as nice as any of those libraries. Usually there's significantly more thorny constraints in them. So like doing a benchmarking comparison is it's great for like, testing out new methods, I think. But in terms of like showing a client like this method versus this method, it's very difficult because basically for the different techniques that you use, you have to model your problem differently. So you're making a different set of assumptions every time you do one of those comparisons. So to me, as a scientist, that's not an apples to apples comparison anymore. But it's like the best that we can do.
I mean, in database, there's a long tradition after people pick it into the SQL language.
Yeah.
There's a set of problems, and then everyone can just compare, and you cannot cheat because it's kind of real business, similar business data. I would like to see something like this driven by, let's say, a consortium of 4 or 5 quantum leaders.
Sure.
Because otherwise, most of the papers are, I took the worst algorithm I could find, and my algorithm is actually better, and it's quantum. And this is not really a science.
Yeah,
Yes.
Yeah.
We need a great benchmark.
Other questions? Okay. I already kind of talked about, I was going to go through some, okay, so I sort of introduced these, so I'll go through them quickly. D-Wave also has clients that rely on our services on a regular basis. That is fairly unique in the quantum computing space. We have Pattison Food Group, NTT Docomo, and Ford Otosan are clients that have taken the optimization solutions that we help them build and have launched them into production. So they're using these applications on a regular basis to solve their business problems. That's another one of those pillars that we kind of talked about, and this is fairly unique in the quantum computing space. So okay, I hate being like the thing between people and lunch, but last thing. So we kind of talked about this, these pillars. We talked about the research that D-Wave is doing. We talked about availability on the cloud, and we'll play around with that later today. And then we talked about commercial applications. The significant takeaway from this is, yes, quantum computing is early stage, but that doesn't mean that there isn't value that can be found in adopting these technologies today. We've seen it with a number of different clients on a number of different sorts of use cases. We're still in early days, so there's still all sorts of valuable research to do, The hardware is still continuously improving. Like we said earlier, we've got all these pieces and now we're trying to put them together. So we're going to see over the next 10 years a significant amount of that. When I started in the space in 2020, there were no quantum computers available on the cloud. So you had to actually sit next to a quantum system to be able to touch it. And now almost every single one of the quantum computing vendors has some sort of something on a cloud service somewhere. So that's just a 5-year change. In the next 10 years, I can't even imagine how things are going to go. So as we talked about earlier, being involved in the space, getting the skills, the understanding of what this is good for and maybe what this isn't good for is going to be a super useful thing as these things are going to continue to change over the next 10 years.
Can you elaborate a bit more on your last point? I mean, let's say you have a company, organization, whatever. In a company, you have so many optimization problems. What would be the way to say these kind of problems are really great for quantum annealer? These are maybe okay, and these are
yeah. That's a totally valid question, and it can be tricky. So when we approach problems, organizational problems, we ask them to describe the problem, and then we look for characteristics like, does it have a lot of decision variables? Like, are we asking a lot of yes/no questions, or are we asking a lot of how many questions or how much type questions? Those kind of lead more to like continuous valued problems, which, okay, not super helpful for the quantum annealing system. We also look at types of questions or types of optimization problems where whatever it is that they're doing now isn't giving them enough benefit. So there's room to improve. Otherwise, there's no point in taking on the exercise. They'll get frustrated. We won't get good results. So we just say, okay, great. It's working well now. Awesome. Continue doing that. Other things that we look for are variables that interact with each other. So it's not quite good enough to have lots of yes/no questions in the optimization, but you need a sort of a yes, no, and then type question. So a yes over here is going to affect the choice over here. So you want those sort of like interaction terms that kind of signifies we want a more complicated problem. That's going to correspond to like the quadratic portion of a cubo and more with the software tools that we have. The other thing is we want problems that are not able to be kind of like enumerated for them to show value. So bigger problems or problems that just, again, don't quite work out nicely for them. The other thing is we also look for highly constrained problems. Oftentimes when I talk to commercial people, they say that, okay, I have an MILP formulation for this, but there's so many constraints that it never converges. Those are the types of problems that we want to look at. Say, okay, how can we remodel this problem using a different set of tools, and then hopefully remove enough of those constraints that we can get to convergence. And the nonlinear solver helps with that. You can take things that you have to model as a one hot constraint in a binary sense, and you can translate that potentially into a list or a set type variable, and then you've taken a whole chunk of binary variables and translated it into one variable with an implicit constraint on the variables themselves. So you've reduced your search space in a significant way, and you get feasibility for free, which is massive for those sorts of problems. So that's the sort of stuff that we look for.
So I have multiple questions, and we have time over the lunch. We don't have to finish all the questions before the lunch. I see the lunch is there and the people become more excited outside. But two questions. One regarding the quantum model. Do you have any available, the gate model? Do you have any available service that does a gate model similar to other companies, or all the available in Leap are the annealing? The second thing regarding access to researchers, because you used to have the free
Oh
account
yeah,
which has
good.
limited and you
Right.
distribute this for anyone,
Sure.
and this is discontinued.
Sure.
So is there like the researchers? I know like anyone is a lot of people, could be a lot of industry people and so on.
Yeah.
But for research, do you have a kind of limited free access
Yeah.
that students can try out things,
Sure.
or like
Yeah, those are great questions. So first question, no, we don't have simulators or software tools available for the gate model system yet. As we build them, we will make them available. So right now we don't have any available on our cloud. We have lots for quantum annealing and building qubos and those sorts of things. Second question about access. We have a couple of programs for researchers and for university courses. You can look on our website for Quantum Launchpad and fill out an application there. You have to describe sort of your research project, but that'll give you 3 months of access for free if you're approved. So you can basically build an application, then take those 3 months, collect data, and use the access that way. Then we also have a program called Voyager, which allows like university courses to have access over a set amount of time. So if you have like 30 students and you want to do like a quantum lab, you can sign up for a Voyager account, and then you'll get some access for those students. Usually not a ton of access. You get more with the Launchpad if you're trying to collect data for a research project.
any other questions before the lunch? So we can grab our lunch outside the room and come back. So Catherine will be here.